about constructing some new conformal field theories. And we did this in 2 dimensions, which is supposed to be a theoretical laboratory where some hard problems become easier. And one of these is the problem of determining how conformal field theories are connected by renormalization group flows. So RG flows start from a CFT in the UV. And they don't have to reach a CFT in the IR, but typically you can tune relevant operators to ensure that this is the case. And in the first example of this that comes to mind, we would work in 3 dimensions and start with just about the only solvable CFT there is in the UV, the free theory. And then use an RG flow triggered by some relevant operator, like phi to the 4, in order to reach some unsolvable IR CFT at the Wilson-Fisher fixed point. Now, in 2 dimensions, things are a bit different because the set of theories where either they have been solved or they can be solved with enough work is much larger. So if you wanted to proceed in order of complexity and solve all the theories you can possibly solve first and only flow away from them later, then you would just never flow away. It would be possible to spend an entire career on the first step. So the set of solvable theories is quite large, and in particular, it contains all of the 2D CFTs that you can read about in reviews. So to make a slightly more precise statement, all compact and unitary, 2 things I'm always going to assume, all compact unitary 2D CFTs discussed at length in reviews are rational. Now, what does this mean? It means that there's some chiral algebra which contains the Virasoro algebra but is generally larger, such that you have only a finite list of primaries with respect to this maximal chiral algebra. If we were to write the torus partition function, it would look like this. Some finite sum of characters with integer degeneracies and to explain the name rational, Vafa showed in the year before I was born that for this to be modular invariant, the modular T matrix needs to have finite order as represented on these characters. And this implies that the conformal weights and the central charge are all rational numbers. They are irrational, and maybe some reviews focus on these and don't brush them aside and immediately focus on the rational radius squared. So maybe my statement is wrong. I agree. And yeah, the next thing to say is that irrational CFTs certainly exist. And the simplest way to see that is to consider some nonlinear sigma model with moduli. And you can make these moduli generic. So the moduli space of a CFT is also known as a conformal manifold. So what you can do is you can start at a rational point on the conformal manifold and then deform away from it to some other point. And as you deform, you're guaranteed to generate conformal weights that are irrational. and therefore a CFT that's irrational by this theorem. So irrational 2D CFTs that are compact and unitary exist, but one complaint you might have is that these examples, the nonlinear sigma models, have some higher chiral symmetry. They don't just have Virasoro, they might have super Virasoro, for example, as will be appropriate for Calabi-Yau manifolds. So this gives an irrational CFT with W not the Virasoro algebra. And if you were to want something generic, then you would want a compact unitary irrational 2D CFT with only the Virasoro algebra. And that's going to be the goal for this talk. It means there's a discrete spectrum. So otherwise, Liouville theory would be an example. So the Virasoro algebra is what you are guaranteed to have in a local 2D CFT, and everything else is a special case. So exactly. So we're looking for 2D CFTs that don't have enhanced symmetry, because the ones that do should be a very small subset. We might like to say these special rational theories form a large set, but it's not large compared to the space of all 2D conformal field theories. So some things that might motivate us would be opportunities to explore more second-order phase transitions. And this is what happened in a similar context in 3 dimensions. If you take some free theory in 3D that has O of n symmetry, and you don't just deform by phi to the 4, you deform by some more complicated operators that are quartic but break O of n symmetry, you can generate a lot of fixed points. This was done by Osborne, Sturgio, and some others, starting in 2017. And some of these fixed points are good candidates for describing structural phase transitions. Another motivation is that having an irrational model will allow you to see eigenstate thermalization, which is the statement that at high energies, the spectrum is exponentially close to what you would get by drawing from a canonical ensemble. And for this one, I'm also going to write gravity, because eigenstate thermalization is related to the no-hair theorem for black holes, if you believe ADS CFT. And just to emphasize one point, a few years ago, the search for a holographic dual to pure gravity in ADS3 became a hot topic. But this is not just about pure gravity. So anything with black holes is going to want the CFT to be irrational. And anything that doesn't have massless higher spin particles is going to want the chiral algebra to be only Virasoro. So eigenstate thermalization is something hard to see. You need to have good control over the spectrum at fixed spin and high energy. But something that might be a bit easier to see is the spectrum at large spin and large energy. And an early result of the analytic bootstrap is that this part of the spectrum for conformal field theories in higher dimensions will exhibit rigid trajectories. And then over the next several years, it was shown that many features of these rigid trajectories actually persist down to small finite spin. And in order to conclude this, it was very helpful to have concrete data from the 3D Ising model. So in 2D CFT, the large spin statement has been proven by these people. But the finite spin statement is wide open. So it would be very helpful to find a concrete 2D irrational CFT with only Virasoro symmetry in order to really understand more about these rigid trajectories, not just the fact that they exist. So that's some motivation for finding some construction of this type of generic 2D CFT, which we can do with perturbation theory, as it turns out. Before we then gear up for a future challenge of using non-perturbative tools to answer some of these questions. And I'll just list a few of those tools. So one of them is Monte Carlo, if the theory in question has a lattice description, and the one I'm going to talk about does. Another one of them is Hamiltonian truncation, which is a different way to study RG flows non-perturbatively in the continuum. You don't discretize space, instead you cut off the spectrum, and people are still working on various clever ways of cutting off the spectrum. There is also the numerical bootstrap. And perhaps most topical for this workshop is that we might be able to exploit non-perturbative constraints of non-invertible symmetries. So non-invertible symmetries, as we've seen in a couple talks 2 days ago, have a very nice interplay with the modular bootstrap. And something I would like to see in the future, I don't know how feasible it is like a merging of non-invertible symmetry with the bootstrap for 4-point functions in CFT. It's worth noting that this has actually been done in a similar context in gapped theories. There's a modified crossing relation that you can derive if you impose the fact that there's non-invertible symmetry in the 2-to-2 scattering matrix. That's a very good point. So irrational 2D CFTs with non-invertible symmetry do exist. But you could complain that the CFT does not is not really generic anymore when it has non-invertible symmetry. I'm saying that if we fulfill this goal, we'll get something that's generic in the sense of continuous Lie algebra symmetry, but not necessarily as generic as you would like. So non-invertible is infinite dimensional, or the chiral symmetry? Yeah, I want to have infinitely many primaries with respect to W, and I want W to be only Virasoro. But yeah, I will cite the paper which first showed that irrational 2D CFTs with non-invertible symmetry exist. And these are irrational 2D CFTs that come from this construction. They're nonlinear sigma models for some collab EL. That was shown by Cordova and Rizzi in 23. And yeah, these are some motivations and tools. And now to be more concrete, the closest thing in the literature to the construction that I'll get into was found in a paper all the way back in 1998, which didn't have much impact at the time, and it's starting to be more appreciated, which I like. And they proposed a candidate for a generic 2D CFT that has some advantages and some disadvantages. So what is that candidate? It is the three-state Potts model n times. So the tensor product of a certain 2D minimal model, plus an interaction term which makes the theory not solvable. So they use the energy operator twice, which I'm going to write as phi 2, 1. And the symmetry group here is something of hypercubic form. So it's the individual symmetry to the power of n semi-direct product Sn. Okay, and there's a coupling constant here. And this was from a group which had done many studies of disordered systems, where it's useful to consider the formal limit of n going to 0. But they also wrote a paper about n going to 3. And they did numerical simulations to show that some observables in this model did not agree with observables in a large list of rational 2D CFT that was available at the time, in order to conclude in an indirect manner that this had to give you an irrational CFT. And they had to do numerics, they couldn't do perturbation theory, because this interaction was strictly relevant. It had a dimension of 8/5, which is not 2. And in pictures, they were at, sorry, I drew this backwards. Well, it's okay. They treated the Q-state Potts model at Q equals 3, where the flow from the UV to the IR was not short. And if you wanted to make it short, you would have to take Q to be close to 2 and fractional, and then you would not be in a unitary theory anymore. So I'm saying that if you modified their construction and you had Q-state Potts models, which has some central charge as a function of Q, it's 1 here. I don't know what it is in general.
Is there something else push?
That's a good question. I don't know what the status of this flow is. Yeah, that's probably worth checking once we have, like now that we can do more numerics. So this is a good candidate, but it's something where you have to use heavy-duty numerics to even get started. Luckily, there actually is a way to get a CFT which likely fulfills these properties, where it has a conformal window with a weakly coupled regime. And that's going to involve higher minimal models, not just the three-state Potts model. So what I'm imagining is that as a function of m, which labels the minimal models, so you can go from 3 through a whole bunch of unitary values which accumulate at infinity, that these unitary flows become shorter and shorter and eventually become perturbative. So I'll just review a little bit about minimal models. I'll consider only the unitary ones, where these relatively prime integers differ by 1. So they have this central charge. And all of the primary operators have conformal weights in the so-called Katz table, given by this formula, where R and S are integers. The primary operators obey fusion rules, which are written here. And there's also well understood non-invertible symmetry in a 2D minimal model. So these, yeah, the non-invertible symmetry comes from something called the Verlinde line. And the Verlinde lines are in one-to-one correspondence with the Virasoro primaries. So they're also labeled by these integers r and s. I really should be walking around with the eraser. And the connection between fusion rules and modular transformations found by Verlinde is that, okay, maybe I'll do it this way. It shows that the action of a non-invertible symmetry topological line on a primary is given by this formula. So in the simplest example of non-invertible symmetry that we learn, it's the Kramers-Vanier duality. So you have this very simple fusion category. You have Z2 symmetry, which looks like this. You have the non-invertible symmetry, which gives you the identity and the Z2 transformation. No, it is in. And then you have this as the last relation in the fusion category. For general minimal models, the Verlinde lines are in one-to-one correspondence with the Virasoro primaries. So you label them in the same way, but you also fuse them in the same way. So I can also write here that this is obeyed by the else. Now, if you stare at these fusion rules for a little bit, you'll see that group-like symmetry is contained in this fusion category, because you can take L m minus 1 comma 1, and this will fuse to 1. Or equivalently, you can take 1 comma m instead of m minus 1 comma 1, because you can choose which half of the Katz table you keep. Either one of these is a generator of Z2 symmetry, so all of the minimal models have Z2 symmetry. And if you go to town on this with trig identities, you'll see that this primary under Z2, it picks up this sign. Like that. So this has been well understood for many years. And the next step is talking about a deformation. So the transfer matrix, yeah, I would need to be reminded as well, but they used very large transfer matrices. Yes. And maybe Paul knows as well, because he's seen me give a version of this talk before. So we can provide some context with the talks from a couple days ago by talking about deformations of a single minimal model. This is a nice subject because some of them are integrable, namely phi12, phi13, and phi15. And the most famous of these is probably phi13 because it gives you the staircase RG flow, which connects one minimal model to the next until you get to the Ising model, and then it's like giving a mass to the fermion description. But in recent years, so this staircase flow between the unitary minimal models, if it gives you a CFT at all, it's going to give you a minimal model because these are the only 2D CFTs that have central charge less than 1. But if you start from a non-unitary minimal model, it's a priori unclear where you're going to end up if you apply one of these deformations. And in fact, there are many more deformations that seem to connect non-unitary minimal models to each other, which have been investigated in recent years. So 1, odd is an example that we heard about. And the initial evidence for this was precisely by matching the fusion categories, because the fusion categories of a non-invertible symmetry give you non-perturbative constraints, which are a lot like Toft anomaly matching. And in fact, you can say that they are exactly a case of Toft anomaly matching. So to just talk about gauging a symmetry, it's easiest to talk about Z2. So let's write the torus partition function where this is time and this is space. And the first step of gauging is projecting onto gauge invariant operators. So 1 plus the Z2 parity over 2 will project onto Z2 singlets. So this projection can be written as the original theory plus the theory with the Z2 topological line eta inserted on a time slice. But then this will spoil modular invariance. And to correct that, you need to add twisted sectors. So you need to add partition functions of the theory with twisted boundary conditions, where now the topological line is inserted the other way. And then there's one more term, which is where all the trouble comes from. So in a lot of cases, this gauging procedure is not consistent because this last term is ambiguous. So what is this? Well, it can either be resolved in the S channel or the T channel. And if the F symbols of your fusion category are such that these agree, then the procedure is unambiguous and you don't have a Toft anomaly. Otherwise, you do. So anomaly matching is how you conclude that in the case of deforming a single minimal model, you might end up on something that's nice. Of course, that's not a proof. It's just suggestive. And there has been more work done in recent years to try to get a proof. And interestingly, that seems to come from the notion of relaxing integrability. So just as the notion of global symmetry has been relaxed in the last decade, maybe integrability needs to do the same thing. A proof of the fact that a non-unitary minimal model deformed by some relevant operator like this can lead to another non-unitary minimal model. So there's currently evidence for this, but it's not on the kind of strong footing that Zamolodchikov's flow is on. But there has been progress, and it comes from relaxing the notion of integrability, and this has been investigated by Ambrosino and collaborators. So there's interesting stuff to be done when you deform a single minimal model. But what we actually did in this work I'm talking about is to take something more like this, where you couple many minimal models. So let's write down what we actually did. We took n copies of the mth minimal model, where we should think of m as being large if we want this model to be perturbative. And then we added an interaction which couples them, called sigma, along with an interaction which is needed for consistency, called epsilon. And they have these definitions. And if you expand this Katz formula at large n, you see that one of these has dimension nearly 1. And one of these has dimension nearly 1/4. So these two operators are close to being marginal, and therefore the flow can be perturbative if m is large. And the question is about what happens at the fixed points. So we can study fixed points using conformal perturbation theory, which is essentially the statement that some endpoint correlation function gets some exponentiated interaction inserted. And these are really bare couplings. So you can choose whatever scheme you like to define a renormalized coupling and determine how that renormalized coupling flows as a function of a short distance cutoff that you use to regulate these divergent integrals. And then you get some beta functions, and you can see what the fixed points are. And two of them are very clear. So there's a decoupled fixed point here. And there's one where only epsilon is non-zero. And if you're at the one where only epsilon is non-zero, then you're just doing the Zamolodchikov flow n times. So the models will stay decoupled. But there are two more fixed points that have positive and negative values of G sigma. And if you look at the eigenvalues of the stability matrix, you can see that this is repulsive, so it has two relevant directions. This one's attractive, so it has two irrelevant directions. And then the non-trivial fixed points have one of each. So you have to do some tuning to make sure you hit this instead of missing it and flowing all the way to the attractive basin. So the idea is going to be to show that one of these fixed points with non-zero sigma and epsilon will be a compact unitary irrational CFT with only Virasoro symmetry. That's true. It's because minimal models have special fusion rules. And maybe a way to say it is that you're preserving a non-invertible symmetry by leaving out those other relevant operators. So if we were to take something like, yeah, if we were to instead do 2 comma 3 or 3 comma 4 or whatever, we would also get something that's nearly marginal, but then we would have some infinite cascade. We would lose control because adding these would require us to add even more, and we wouldn't know what to do. So that's a good question. We think this has not been discussed before. The vertical line, yes. This is going to be, so instead of m plus 1, it's going to be lower. It's going to be m minus 1 m to the power of n. But in order to study these non-trivial fixed points, we're going to make use of one more fact from modular invariance, which is the Carty formula. So the density of states at some high dimension delta is given by, I think, this formula. And with a modified calculation, you can show that the density, not of all states, but of the Virasoro primaries, is given by a very similar formula where you just change C to be C minus 1. So if you have a theory where the central charge is greater than 1, and this is such a theory, it can be as large as you want, then the density of primaries grows with the scaling dimension, which automatically means there are going to be infinitely many. So this has a central charge greater than 1, which means it has infinitely many Virasoro primaries. So now the two questions, how many primaries are there and what is the chiral symmetry, these are no longer independent. We can show that this model has only Virasoro as the only chiral symmetry, and then it will immediately follow that it's irrational. So now the goal is just to figure out what the chiral symmetry of this model could be. So if the coupling is 0, if we're here, then it's very clear that we have more than Virasoro symmetry. We have n times as much. We have n copies of Virasoro. So a decoupled fixed point will have Virasoro to the n, and this will be generated by individual stress tensors. And we want to show that a non-trivial fixed point has only a single Virasoro. And I'm going to call that Virasoro hat. It'll be generated by the stress tensor, which is the sum of the separate ones. And that means that when we use perturbation theory, we'll need to show that a lot of currents here break. So we'll need to show this for the individual t's. But we're also going to need to show this for many polynomials that are built out of these individual t's. One of these polynomials I'm going to denote using this shorthand t with a capital index. And what we're going to want to show is that this is only 0 when all the couplings are 0. If the sigma coupling is non-zero, then this should have some source term written in this way. So this, okay, let's write it in this way. Plus higher order corrections. This denotes that it's a bare coupling. Yeah. Yeah, in everything I'm going to do from now on, I'll be working with renormalized couplings. Yeah, I would say no. They're not. It's not that one is going to be minus the other. Yeah. Yeah. In fact, we had. So I'm not going to talk about this, but we looked at some operators that are not UV currents. We looked at some double twist operators, you might say, and for this analysis, it was important which one we were looking at. So the goal will be to show that all of the currents, all of the UV currents, other than the ones that are going to land in this Virasoro hat module, break. And we're going to do this by making use of this equation of motion. And this equation of motion can actually give us some powerful non-perturbative constraints as well. So you might know that in addition to studying the 3D Ising model in a 4 minus epsilon expansion, some people want to study it in a 2 plus epsilon expansion. But the 2D Ising model has higher spin currents. It has Virasoro symmetry. Those Virasoro symmetry currents are going to need to break when you go towards 3 dimensions. And yet, it doesn't have, the 2D Ising model doesn't have any operators that can play the role of the source term on the right-hand side. So whenever this has conformal weights of L comma 0 in the UV, this is going to need to have L comma 1. And that means that any proposal for the 2 plus epsilon expansion that recovers the 2D Ising model as epsilon goes to 0 is immediately dead. It would need to recover 2D Ising plus a decoupled subsector to supply this. So the idea of using this non-perturbatively was put forward by Richkov and 10 years ago. Well, I'm just pointing out that this has untapped potential, even though we're going to use it perturbatively. So we want to show that all of the currents that would have to break pick up some anomalous dimension. And if we were to do this using vanilla conformal perturbation theory, this would be a hard calculation. Because the one loop anomalous dimension is going to come from this kind of a 3-point function. So this anomalous dimension matrix. Which is automatically 0 by chirality. So we're going to need to do look at the integral of a 4-point function, which is conditionally convergent and very time-consuming to evaluate. Sorry? Yeah. Let me check how much time. I'm almost out of time. I need to speed up. So this is useful because it allows you to compute anomalous dimensions. So the first thing is that you can find what B is. I was vague about what it is here, but there's a way to find it. So you take so you use the equation of motion on this quantity. You get you get this mixed correlator, which can be evaluated with a very simple calculation in conformal perturbation theory. Note that this is an anti-holomorphic derivative of something holomorphic, so it's a delta function, and you just get pi times g sigma times a matrix of OPE coefficients. So that lets you find B. And then once you know that, you can get anomalous dimensions, because you can take this equation of motion and conjugate it using the fact that this derivative is L bar minus 1. So what does that look like? Where this is now 2 L bar naught. So this knows about anomalous dimensions now. And it's common to find formulas for the anomalous dimension in terms of the coupling from this method in the case where you have just a single current that needs to break and a single current that can do the job of breaking it. But I want to write down what you get in the general case, because we have a large degeneracy of currents in this n-fold product of the Virasoro algebra. So we start by generating a basis for those currents and a basis for the space of operators that have the right quantum numbers to recombine with it. And it's convenient to allow this basis to be not orthonormal. So the operators we start with are going to be related to the scaling dimension eigenstates by some matrix which is not orthogonal. And what we're going to want to do is use the polar decomposition on it. So this is Hermitian and this is unitary. And then what this equation says is that the anomalous dimension matrix in terms of this it's going to be the inverse gram matrix for the V's conjugated by this OPE coefficient matrix. And then we just put H inverse on either side here. And that means that if we know H, then the anomalous dimension matrix, which we're free to diagonalize, is given in terms of data in the decoupled theory by this formula. And we do know H because it needs to be such that the outer product of these M's is equal to the gram matrix for the T's. So H is going to be some square root. The square root of a matrix is not unique, but if we demand that it's positive definite, then it is unique, and it can be found by spectral decomposition. So given an arbitrary basis for these types of operators and these types of operators, restricted to some finite dimensional subspace labeled by spin, we can compute anomalous dimensions. And that's what we did until we ran out of computer power, which happened at around spin 10. But the results up until spin 10 were quite promising. They showed that all the currents outside Vir hat up to spin 10 they broke for n greater than or equal to 5. And the code for this would be tedious to describe now, but it's online. Anybody can download and run it. What's a little bit more interesting is describing the checks we were able to do to make sure that the code was giving trustworthy results. So one of them was about generating a basis for the t's and the v's. A zeroth order check is, do we generate the right number? And we know how many there should be because the decoupled theory has a partition function, which is just a single minimal model partition function to the power of n. So we can extract some results for the degeneracies for each Sn representation. And at first I was doing this for some very small representations, getting some piecemeal results that were not very systematic. And I'm very grateful to Antonio for not being satisfied with this and driving a beautiful formula. So he showed that for a particular representation of Sn, the refined partition function is given by a sum of group elements, where now we take the character for that group element. And then add the type of twisted partition function that's over there. And this twisted partition function is the only model-dependent part. This is the part that depends on how Sn will act. And in this story, it acts in a simple way. It's going to use the fact that this representation is labeled by a Young diagram, and you have this product up to the number of rows of the single minimal model partition function evaluated like this. So this check works. Another check is, what about n equals 4? We seem to find that some currents aren't going to break. Well, for n equals 4, there is actually a result that when you have only the sigma deformation, so when you're flowing to a gapped phase in that way, there are some dualities you can exploit to show that this flow is integrable. So Leclerc, Ludwig, and Massardo showed that the pure sigma deformation is dual to what's called an integrable Toda theory. I don't know too much about these models, but they're labeled by extended Dynkin diagrams. And the extended Dynkin diagram of D4 looks like this, where you can think of the nodes as being the individual minimal models before you couple them here. And that's consistent again. So finally, the last thing I wanted to talk about was that if you were to find some other construction of a candidate irrational CFT with only Virasoro symmetry, one way to see whether it's the same as this model, or another example, is by matching the fusion categories yet again. So we should see which Valinda lines commute with these deformations sigma and epsilon. And that turns out to also be different depending on whether n is 4 or greater. So for n greater than or equal to 5, what you have to do is take a product of Verlinda lines where the second index is 1 and the first index is either all even or all odd. But for n equals 4, there's one more thing you can do. You can have 2 even and 2 odd. Like that. So that's the status of where we are. I think I'm over time, so thanks a lot for listening. Paul? Well, we had enough faith in perturbation theory to think it exists. Because as m goes to, yeah, as m goes to infinity, these, yes, okay, so let's say that if these are finite distances that I'm drawing in this plot, then they're really finite distances for m times the coupling. So the coupling itself is of order 1 over m, so it's very small. We see that it makes the beta function 0, yes. Yeah, it's the one loop beta function. Exactly. Not yet. Yeah, yeah, exactly. That's what came out of the this integrability paper, actually. Yeah. I don't know if it's known. Yeah, it's worth saying that even though we found that at 2 loops, so this is a, like the point of this equation was that it allowed us to look at 2 loops with only 1 loop methods, so to speak. At 2 loops, we found anomalous dimension eigenvalues of 0, but we expect that at 3 loops, there's still going to be non-zero, even in the case of n equals 4. Yeah, then there might be especially powerful methods we could use. So m had to be large for us to trust perturbative results, but there's going to be a conformal window, and a question is how small can we make m for this fixed point to exist and for it to be irrational and so on. They're not. So yeah, like for what we did, looking at the currents, we just had a fixed point coupling, and then we would say, okay, the anomalous dimension is non-zero in terms of the fixed point coupling, and we can plug in this one or this one. But at higher loops or for other observables, things might depend more sensitively on which one we're in. Yeah, it will be a flow to like a TQFT. So perturbatively, I guess the minimal models we start from are unitary, and then yeah, I think that's like a special pathology with free theories. The potential is 0, and you can make it unbounded from below um, with a bad deformation, but here we deform around an interacting theory. I think there's less that can go wrong, but non-perturbatively there might still be things that can go wrong. Yeah, this construction is very flexible because we don't have to preserve Sn. These were chosen to be the nicest ones. Um, these are invariant under permutations, but something to do is yeah, construct operators that are like this but don't preserve Sn. Yes. Good. So it seemed that getting a small number of nearly marginal operators was harder in that case. Um, you can get operators that are classically marginal. They have dimension 2, and um, like a common one is JJ bar. So if you didn't want the dimension to be a little bit less than 2, but you were okay with having it start off being exactly 2, this would be a very natural one. And so for a single Western-Witten model, the flow by this operator to some like parafermion theory has been studied, and it's quite rich. And there's also something by Kostas Svetos and some collaborators that might be worth mentioning. No, this is one. Well, it's yeah. You make a square where you have like j from one copy times j bar from another copy, and this can be shown to be integrable. And there are various games you can play, some integrable models you can find that way. There's not a super strong connection to our work that we've found yet, but there could be later. Um, I don't think these ones can be. The I mean, sort of related to what you said, like outside, like in the rest of the CATS table, if you don't use like 1 comma 2 and 1 comma 3, you get all sorts of light operators for large n. There is a version of this story you can make with minimal models of a W algebra, because there is some holographic duality due to Gabriel and Gopakumar finding some like higher spin gravity dual of WN minimal models, and then yeah, the coupling of them should have a gravitational interpretation.